So, next part is looking at different views on image analysis and looking at the, let's see, I have missed somehow a header, but I would say this is, yeah, in principle, image analysis, images is a bucket of pixels, and how you choose to turn it depends on what your background is. And here you can see that you have the experimentalist, you have a computer vision approach, and you have a deep learning approach. And depending on what your background is, you would probably also analyze the images differently. And looking at the experimentalist first, you have a very problem-driven approach, top-down. You will have a real reality-based model. You know what you actually have. If it is a human body or if it's some kind of mechanical device, at least you know what it is. And it could be that you want to count cells. Could also be that you want to look at the porosity. If you look at, for example, geological samples. Then we have the computer vision. And then it's method-driven. So you look at different algorithms, how to work. You are feature-based. You look at more at the image as some kind of intensity model. And it's a way that you also sometimes you engineer features for solving your problems. So can be different. So features that you engineer is edge information. So you look at edge detection. And that could lead on to face detection, that you identify which face it is. And then we have the deep learning approach, which is result-driven, because all these machine learning approaches, they are based on some existing knowledge. You have to train your model with some data before you can get your answers for the big questions you want to answer. So it's actually redesigning the thinking of how image processing and analysis is doing, because you have really different approaches, but under the hood, it's anyway very similar math to the computer vision approach. But you don't see it in that sense. And what you do would be that you put captions on images, and can also be used to identify unusual events in your data. And now that leaves us now to how images appear. And that actually goes over to a little bit more the technical part of today's lecture. So we have the image formation, which is based on some kind of excitation. You have a sample, and the combination of them give some response, and that response is then acquired by some kind of detector. And depending on what you're doing, what kind of source you're doing, you also get different responses. So it could be that we are working with visible light, like in microscopy. It could be X-rays, electrons, even a sharp point. So you have this surface sensitive cantilever measurement. Also sound waves are used for this. And each of these techniques, they have different interaction techniques, concepts. So with the X-rays, you're looking at electron shell levels or electron density and so on. And also the response that you get could also be different. Could be absorption, could also be reflection, phase shift, scattering, and so on. And the detection also varies with the kind of source you're using. So it could even be with light, your own eye. Could be light-sensitive film. But what we are more looking into are electronic devices that can capture the information. And then we are talking about CCD cameras, CMOS. We need maybe some kind of conversion, like a scintillator, which converts the radiation into visible light for then capturing it with a camera. And Here is a table of where different images come from and what their characteristics are. I'm not going to read the whole table, so that I leave for you. And then we have our acquisition of images, and the typical way of getting images is that we have direct imaging. So we have some original objects that we are shining through. We do a measurement, maybe blurred for some reason through the imaging system, and that needs to be reconstructed. And maybe the reconstruction is not always as good as the original. We don't know it actually. Or sometimes we can measure it with another technique, but that technique is maybe not suited for what you want to do. Indirect and computational imaging is a little bit different, because here we record something in, I would say, acquisition domain, and then through computation you can get the image you want to see. And here you have one example of it, where the measurement maybe is done in the Fourier space, and in order to really see the information you want, you have to do an inverse Fourier transform. And that is actually one way of doing tomography, is actually doing the acquisition in the Fourier space and then do the inverse transform. So with the traditional imaging, we have some light source or some source. The light goes through a lens and then it's shown on some image plane, and that is what we are registering. The model that we would work with is maybe a bit more complicated, and here you can see we have some convolutions and multiplications and so on, and in the end we maybe even have some bias signal that is coming in to the system. So this is more what it actually looks like if you want to start doing a modeling of the system. And if you do color imaging, then you have, it's even more complicated, because then you even add a lambda here. So every wavelength has its own response through the system. Could be that you have maybe colored filters in your system that cuts out some parts of the wavelength. Could also be that the sample itself reacts differently at different frequencies or wavelengths. So there is a lot of complexity that can be added if you do polychromatic imaging. And with the indirect imaging, here you have different examples. One is the tomography, where you do a lot of radiographs around the sample, and then in the computational step you can reconstruct the three-dimensional volume. Or you can also look at hyperspectral or imaging or light field photography. It's actually quite fun, because there in the computational step you can actually compute the depth of field within this movie. I'm not showing the movie now, but you can click on it if you like. Or it can also be surface topography. So here we have a little needle that goes over the sample and measures how deep it goes, and that gives us the image. So now finally we come to the images themselves. And first of all, a very abstract way of seeing what an image is. It's a pairing of spatial information and some kind of information. So that would be intensity, could also be a vector. So on each position we have a value. And typically what we are working with are two-dimensional and three-dimensional images, but it could also be four-dimensional if you want to go push it that. And if in 3 dimensions, of course, we have the volume, where we have the coordinate axis x, y, and z. And usually it is on a grid, and then we have some numeric value. But it could also be that we have x, y, and time is actually also, so a movie is actually a three-dimensional image. And the image, real world, is continuous, but our images, to get them into the computer, we need to do sampling. So putting it in some kind of grid. And there are different levels of sampling. One is just the intensity, which in reality is some continuous curve. And space also is continuous. When we put it into an image, then we instead have discrete values. So we need to sample the gray levels or the intensity into a given number of levels. Typically, what we are working with are 8-bit, 16-bit, and 32-bit images. And then, of course, the image itself also need to be subdivided into some grid. Otherwise, we would blow up the memory. And what does this spatial sampling mean? Execute, bitte. So, with the light now, it's difficult to see. Oh, wrong one. Nope. So, hope that is better. Here I show some examples of spatial sampling. Here I have the original, which I downsize by 2 by 2. Then you don't see much difference. But if I downsize by 32 by 32, so every pixel is actually 32 pixels in each direction of the original, then it's getting very pixelated. You can really see the big squares here. And also it's very hard to see the information. And we can also do resampling in the levels. So the original one, I think, the original is actually 16-bit. And that one I reduced to 16 levels, so that would be 4 bits. It's still quite okay, but you see that you start losing a little bit of contrast. If you reduce it even to 4 levels, then you can see that it's really difficult to distinguish much in this image. That's only 2 bits, so it's not very much. So it's a very high compression, but it's maybe useless. And important is to distinguish between pixel size and resolution. So pixel size, because that's confused in actually many commercial products too. People are talking about this screen has a resolution of 4K or whatever. That's not the resolution. It's actually the pixel pitch, or the pixel tells the pixel size and pixel dimensions. So the pixel size is the pitch between the pixels on the grid. And it's also representing the smallest area you can represent in the image. And the resolution is rather related to the optical system. So it's more about what combination of lenses, did you have some scintillator, etc., that makes the image a little blurred. And it should usually be a greater value than the pixel size, because otherwise you will not fulfill the sampling theorem. And that's actually the smallest size of object that you can see. It's determined by the resolution. And what happens when we... I should have run all these things actually before. So what happens when we represent the same image but with less pixels is that you saw before that we get very blocky information. But here you can see the difference, what happens if we have different resolutions at the same pixel size. So in this case, it's a very sharp transform. So you go from black to white in 1 pixel, bam. And in this case, which is more realistic, is that you actually have a smooth edge in your image. And that is what you have to work with when you do your analysis. So there is a limit on how small gaps you can see. For example, if you have 2 grains and the resolution is not sufficient, you cannot distinguish if these grains are touching or if there is a gap between them. And yeah, that one I actually already showed before. And then we can look into how many bits are really needed for different representations. And it depends, of course, on what contrast differences you want to look at. And also within each contrast range, how much variations do you want to see? And how many different sample features you want to detect. Then, of course, you have a little bit the question, a numerical question, sensitivity to rounding errors, because you're doing a lot of computations here. And when you do that, there can be the problem that you lose information in the rounding. So looking at few bits, you require high contrast images, must also be clean images, and it's mostly used for segmented data already. Many bits, then you can have less contrast in the image or in certain regions. It's also useful when you have noisy images, and I would say you always have, because we are living in nature and we have counting noise from the detector systems, etc. And also, if you want to see gradual changes within the sample. Floating point is when you have really high intensity dynamics, and if you want to quantify physical properties from the gray levels. So what we do in neutron imaging, for example, we try to very often to quantify the amount of water in the sample from the gray level. And then, of course, floating point is very useful in algorithms. So you do the main computation in floating point, and then at some point you flip back maybe to 16-bit when you store it. Looking at a histogram is our first way, the first analysis we are doing on an image is just to see the distribution of gray levels in an image. And this looks something like this. And when you do it in Python, you have here you compute a histogram, and added a little bit of padding here. So we are actually using 2 panels. So we use subplots here, and then I do some nice decorations with label axis labeling. So if we execute this, what happens? We see a histogram, and I need to move up. Nope, I don't. No, it doesn't want to move up. Okay, that was unfortunate. So now we see it. So from this piece of wood, it's actually a piece of petrified wood, you can see that it has a quite wide distribution of gray levels, and then there is a huge peak. So if you look at this histogram, where would you say that the huge peak, what that would correspond to? So what you see on the axis here is the image value, so which goes from 0.4, which is dark, to 1.0, which is bright. So what is the high peak? Yeah, so you're in the middle in green. Yes, so that's the background. And often we don't need that, because that's just the background. So we try to maybe to sort it out. And then it's harder to actually say what the different pieces are in this distribution, because we have very gradual changes within the sample. So here are some arrows showing where the different regions are in this image. And it's actually what I do when I get a new image is the first thing I'm doing is more or less looking at the histogram. What does it look like? Can things be clearly separated, or is just one single blob? Which means essentially you have very noisy data. And the idea is that we want a histogram where there are more distinct peaks, because then we can identify more regions within it. And here are some examples of histograms. And again, I need to... So, here we can see some examples, and this case, it's just slightly noisy image. It's a test image where we more or less have only black and white and a little bit of gray levels, and you can see, of course, we have a lot of black. Then there is a little bit in here, and that would be corresponding to these insets. And then there is the background, which has some noise distribution. Natural images are never so nicely, or very rarely so nicely separated. So what you can see here in this image of a camera, it's almost uniform distribution, so it's very distributed over all gray levels. Another way of seeing a histogram is the bivariate histogram. So if you have different modalities that you're looking at, in this case I'm looking at X-rays and neutrons, then you can see for each pixel you can actually count the gray level, and that gives you this kind of histogram, and it makes it, in some cases, it makes it easier to distinguish different categories in the data. As you can see here is the neutron histogram if you just look at the neutrons, and here you can see the X-rays if you just look at the X-rays. But it's hard to distinguish, for example, this little peak here, which would correspond to the interesting information, which is the root. But with the bivariate histogram, you can actually see it. This is something I'm going to talk more about in lecture 10, I think. And visualizing gray levels is always the problem, because you and I can not resolve so many. And here you can see, oops, sorry, what 8 level does to us. We can clearly see it. 32 levels is still possible to see, but if we go up to 256 levels, it's just a smooth gradient that you see. So you have to be aware that the more levels you use, the harder it is to distinguish the individual ones. But it's actually often not so relevant unless you have very subtle changes in intensity that you want to detect. But for that, we actually can work with the visualization of the levels. So we can play with the brightness, that we only focus on certain regions like this. And if you look here, you will only see some of this perimeter of the object. And if you look here, you can see more the boundary. So you can play with the brightness and also the contrast, which is how wide this window is. And with that, it's easier to explore the data. And this is in principle only a visualization thing. You should rather not truncate the gray levels, because then you lose information. And here we try to create a little image. It's just a random image, and it's not so exciting actually, but it's an example how you can do it. To begin with, the image is actually, as I said before, a mapping between position and intensity. So here we look at only the first 5 of this image, which is 5 by 5. And you can see that every pixel has its own value. And using the same data now as an image, we can see that when we map now the coordinates and put the values on them, we can even visualize which grade level it has. The value can of course only be visualized if you have very blocky pixels like I have here. If you have the full image of a 2K, then it's not possible to showing the numbers, of course. But if you zoom in, sometimes it can actually be relevant to look at the values like this, because you can also make some qualitative decisions in how well your detection algorithm is working or something. Another way is also to apply color maps to the image. And well, it's more interesting maybe to look at it. And in some cases, it's even easier to detect features if you apply a color map. So we have looked at before mainly the gray level image, but we can also look at what it looks with different color maps. We can have something in the blue range. So this one is, I think, ranging from black over blue to white. Then we have the traditional rainbow map, and here is a map called Viridis or Parallel, depending on which tool you're using. Parallel is for MATLAB and Viridis is for Python. And then we can put some colors on, pseudo colors on real images. So looking at our piece of wood again, and then you can see what it actually does to your visualization, and that you can easily spot different regions, and they still have a relatively good contrast. And of course, it's the question of what you really want to see and which color map you choose. Actually, the jet map, that was long time the default in many tools, is not so good because it doesn't print well, and it's also not good for colorblind people. And sometimes there are troubles in interpreting what it actually means. So the new developments actually going towards this over blue over green to yellow color map that is more popular nowadays. And that is done in principle using lookup tables. So where we have some intensity and map that towards a color. And we can look at many different color maps, but in principle, what the what's called perception science is saying is, please don't use the rainbow. And we can also show what different color maps look like. Yeah, so here we would have a lot of variations. These are the color maps that you can find in Python. And usually they are enough. Typically, you can see here that you have some color maps that are going from on discrete levels. That is more useful when you do segmentation. And then you have more gradual changes, like here. And then there are some plus-minus maps, can also be useful, but when you use plus-minus, you have to make sure that the data is scaled correspondingly. Otherwise, the switch point, the 0 point, is on the wrong place, and then it can be quite misleading. I should have run this all these cells. So here you can see how the different color channels are mixed to get these different colors. And I'll skip that one. And then we can look at, here is an example where we look at a real image where we use first the grayscale, and then we use one called hot, which goes from black over red to yellow. And then there is also some logarithmic lookup table, which can actually be quite useful because that compresses the range in a way. And features like these, very dark features, are now enhanced in a good way. So that can be a way also to enhance the contrast and make it easier for the eye to find things. With images, so until now we have only talked about pixels and how to work with them. And now we switch over to how we can actually do operations. So we have pixel-wise operations, which is the arithmetics. So we can do image plus image and get something out of it. Can also apply different functions, sinus, exponentials, logarithms, etc. And in a collective sense, we can also use statistical functions, computing the average value, standard deviation, min, max, median from the whole image or regions of the image. And here we have an example where we do a typical operation in imaging, is that we have an input image which is made under certain light conditions, and we have a bias caused by the dark current in the detector, so we have to subtract that, and then we have the illumination field, so that's the open beam, and that one of course also has this DC. So if we look at this example here, we load some images, then we do the norm, and then afterwards we visualize it in a nice way. So executing that, we can see what they look like. We have down here the sample, and you can see that it's darker towards the edges and then it's bright in the middle, and that is because of our open beam that has that shape. Dark current, right now oops, where am I? I'm lost, I'm in the wrong place. So now I'm in the right place. So the dark current is usually just noisy on a quite low amplitude. And then afterwards we have this normalized image where you can see that the whole background now is flat. And this is actually the kind of image we use then for the analysis. 3D images is stepping it up one level. So it's just that we have a three-dimensional matrix. And that can be either volume data, or it can also be time series data in 2D. And they can be processed in the same way in many cases. So for example, if you want to apply a filter, you can actually also apply it, a 3D filter on a time series. That is left for lecture 9, I believe. And creating a volume image, we have here some volume where we create the whole volume, and I'm not printing this now. And you can also show it in a way. So the typical we think about is the beautiful 3D renderings, like the little gold piece I showed before. But another way is actually looking at the slices themselves. And here we have a tool called Montage 2D, which takes the slices and spread them out on a matrix in the plot. So it would look something like this. No, it doesn't. Oh, I need to load it. Okay, then I need to go back. So then we go to the next. And then it should work. Yes. So then with this montage, we actually print out all the different slices like this, and we can have an overview of what's happening within the image. The 4D images is more advanced, and you have also the analysis of 4D. Then you have to put your brain into it and getting the coordinates right if you want to do a full 4D analysis. But in principle, what it is a time series of volumes, mostly. And then we can even have multiple values on each pixel. That could be a spectrum. It could also be just some kind of vector field that you look at. And here you could have, for example, intensity and transparency in one image. And then is the question how to visualize these. You can, of course, look at them separately, or you can combine them somehow. But here in this case, we look at intensity in one case and transparency in the other. And there we come. Hyperspectral imaging is actually what I mentioned before, just a spectrum. And here we have a case where you can see each point in this image actually correspond to a full spectrum of wavelengths. And then the interpretation can tell us about material composition within this sample, for example. And another application would be in neutron imaging. We're looking at crystalline structures and texture in the materials. Then we also look at the full spectrum of neutrons within the image. So looking at the pixel values, I really have to, so here we have, in this case of this multispectral, you have some wave number and you have a value. So this is the information that we have for each image. And the question is how you organize it. Sometimes you can do it actually as a 4D image or 3D, where one axis is the wave number and the other axis X and Y. And finally, to round off, we have, as you have seen, we have this large amount of data, and the question is how we work with it. And one thing is, with a lot of data, we should go parallel. And following Moore's law, our CPUs get larger and larger all the time. And Moore's law plots like this. And you can see one thing is that the number of transistors always increase, but the clock speed is actually at some point staying at 3-4 gigahertz. And actually it doesn't go beyond that, because then we play with the light speed more or less. So it's not possible to go beyond the clock speed, but number of transistors can always increase, and that gives us our multi-core CPUs, which we all have nowadays. And what we can do also is not only the CPU, we can also use the graphics card and using GPU processing. And of course, this makes it very important to have parallel code. And the larger data you have, the more you have to make sure that you have code that is running in parallel in some sense. Could be locally on your computer or your graphic card, or you maybe even have to go up on a cluster or cloud computing. And that is what I'm going to talk about in lecture 11. And what we can do is actually we can send out it on the cloud, and there are a lot of resources to do this. Some are free or half free. To begin with, they are free, but then when you're like an entry drug, once you know what you want, then you have to pay for it, because then you start using a lot of resources. But it's not that expensive to buy these resources. So it's, for example, as a comparison, a PhD student in Switzerland is about 400 times more expensive than per hour than renting a slot on Amazon EC2 machine. So it's really worth considering if you need to crunch a lot of data. Could be also doing machine learning training. It's maybe worth considering buying some time on these computers. Because one thing is having your own workstation, but as soon as you start thinking about setting up your own cluster, then you have a lot of maintenance, and these machines are usually not fully utilized, so that becomes quite an expensive solution. And well, just as an example, what parallelism means, now I'm going to make food, so a simple soup. Hope you don't get too hungry because it's not yet lunchtime. But anyway, what the workflow we have is first we buy some ingredients, in this case carrots, peas and tomatoes at the market. Then we go on to the butcher and buy some meat. Then we chop our carrots into pieces, followed by chopping the potatoes in pieces. We then heat the water and we wait until the water is boiling, and then we add the chopped vegetables. We wait for 5 minutes and then we add meat. So, clear sequence. This is what we would do to begin with. But the next step would be to do a little bit more complicated, and now we can actually do things in parallel. So we could mix up carrots and potatoes, then we can add some egg and mix it and fry for 20 minutes, and then we do something. Yeah, so it's in general a more complicated thing. And here is the question how to work it up. And the easy workflow is just like this, long sequence. And if we do it the more complicated way, we can actually see you can do things in parallel. So you can buy the vegetables while the water is heating up. And then when those are available, then you can add the vegetables to the soup. And while you do that, you can actually buy the meat also in parallel, and then you can add the meat to the soup. And here you can identify that there are different workflows. In principle, you could do things in your image processing analysis that you do, say, a lot of filtering, but you have many images, so you could actually filter each image separately. Or you could also do one track is doing one part of the analysis, and the other part can do the other track of the analysis. And if you can split it up in a good way, then you can actually gain time. And for that, there are a lot of tools already developed, something called DAG, Directed Acyclical Graphs. And there are a lot of toolboxes doing this, some with graphical interface, other ones you have to program. And so some of them you may even have heard about, like TensorFlow or PyTorch. Some may know also KNIME, which is a graphical user interface where you more or less with small boxes and threads connect your program. Yeah, so those are the different ways. And this can also go into the topic of deep learning, which can also be split up in a parallel manner very well. And today, most deep learning packages at least use the graphics card for the speed up, because it's a lot of repetitive calculations which are very similar. And in some cases, it's also implemented on clusters for the larger networks. And well, that was it for today. And in principle, we have started talking about what images are and how to work with images a little bit, or defining images. And also pointed towards that science with images is not always so trivial. It's quite a time-consuming work, and you need to think about how to put up your analysis. Next week, I'm going to talk about data sets and what to do when you don't have sufficient data for your analysis. And one thing I didn't add here, I'm also going to add a little technical section about data frames. So that was it for today's lecture. After the break, or actually you can start directly if you like, we are going into the exercises. And today I'm going to support you. And the first step we are doing is getting you up and running with Python Anaconda. So the question is, how many have worked with Python Anaconda before? So quite many, actually. Most of you. Good. And what we are going to do is also some basic getting to know Python, how to program with it. I'm not sure. No, I don't think there is so much images in this. There is a little bit images in the end, but not so much. So yeah, that is what we are going to do as a next step. And then I assume everybody of you have already installed Anaconda on your computers. So you don't need help. Okay. Anyway, that is what we are going to do today.